So now we're going to revisit this notion of robust standard errors. If you recall the discussion in class, in the classic OLS estimation, the estimate of the standard error of the OLS estimates was an estimate of sigma squared times x prime x inverse. But that was only in the case where we assumed that the error terms were IID. So they had the same variance, the sigma squared, and they were uncorrelated. Now, if they're not homoscedastic, so the variance is different by observation, and if they're correlated, then that no longer holds. And then we saw, I have this in my head, you guys may not, but it's x prime x inverse, x prime sigma x, x prime x inverse. It becomes this monster thing, right? And then we said, we cannot estimate sigma because sigma is n by n, that's too much. But we can estimate x prime sigma x, which is k by k, which is much smaller than the sample size. Remember, I said estimation is all about winning the race. So if your number of observations increases, but your number of parameters does not, then you're winning the race. So in this formulation, the number of parameters, so to speak, is a k by k matrix, whereas the number of observations is n, and n can go to the limit. Right? And there's this really major result in the early 1980s in econometrics. And as it turns out, there's a counterpart in statistics, but they didn't know about each other, which is called a sandwich estimator or a white estimator, which approximates this x prime sigma x by replacing sigma by the squares of the residuals, sometimes with an adjustment factor. So for small samples, this adjustment factor really matters. As the sample gets larger, it matters less and less. spreg doesn't support the adjustment factor yet. No, maybe we'll put that in later. So if you want to correct for heteroscedasticity of unknown form, you do this adjustment. And so then instead of doing naively x prime x inverse, you do this whole thing with the x prime sigma x matrix estimated. And that's what we call in spreg the white estimator. Okay. So the first option, the standard option is to do the classic standard errors, so nothing changes. And just to repeat, this is already in the notebook, but just to show you the standard errors, this is the classic case, right? These are the standard errors. And so now we're going to set robust equal white. And here are the standard errors. So this is 11.239 compared to 8.966. 4.82 compared to 4.43. And then 3.49, robust is 3.39. Oh, this one is smaller. So this can be very confusing. In general, the robust standard errors tend to be larger than the classic ones, but not always. Okay. So it's not a hard and fast rule, but it's a general tendency. So we're correcting. The question is always, what are we correcting for, and are we overcorrecting, right? If there is no heteroscedasticity, there's no point in doing this. But then, even if we do it, it won't make a big difference. Right? If there is heteroscedasticity, then you see the difference. Then the standard errors after the correction will tend to be larger, sometimes much larger than the original ones. Okay. So we can do this in an ordinary least squares regression, but by the same token, we can also do it in two-stage least squares. So it's the exact same setup. We So again, for reference, I have the two-stage least squares regression here with the standard errors. And now I'm going to say robust. It's all the same stuff. So y, x, y and e and d, q, these must be specified for two-stage least squares. And then one option is robust equal white. And again, this gives us the robust standard errors. In this case, some of them are actually smaller. Right? So again, this is not hard and fast, but in general, the robust standard errors tend to be larger than the original ones, but not always. The only difference between the OLS case and this case is that in this situation, you use two-stage least squares residuals, not ordinary least squares residuals. So it's all the same setup. It's not. It's a little more complicated because we don't have x prime is sigma x. It's a much more complicated expression because it has the instruments in there. I don't know if I showed this in class, but it's a monster, right? So that is all gets computed using the residuals from two-stage least squares to estimate this K by K matrix. It's still a K by K matrix. Okay. So that's the first type of robust. I would say in most cross-sectional situations, by all means, do the correction and see what effect it has. If it has little effect, not to worry. Typically, if you have very strong indication of heteroscedasticity, then the correction will make a difference. Okay. So that's one type of correction that addresses the problem of the variances not being constant. Now, what if there's also correlation? Then we saw in class, there is a solution to this for time series. And the way to think about it is that you compute covariances, but not all of them, because you can't. So you have to kind of simplify the problem and compute covariances up to a range in time. And you make the contribution, it's an average of all these covariances, you make the contribution decrease as you go further away in time. And Collegian and Prucha took this principle and transposed it to the spatial framework by using a kernel function. We talked a little bit about kernel functions. They're actually weighted averages of observations that are within a given distance band of each other. That's called a bandwidth. And there's a distance decay, again, smaller weight as you get further away from each other, that is specified by the actual kernel function. And a triangular kernel function has a linear decline with distance, so that when you hit the bandwidth, the weight is 0, you're done, right? The others are either steeper or not as steep as the triangular function, but they're all forms of weighing differentially as you get further and further away from each other. As the distance between the pairs, remember these are covariances, so you need two. The distance between these two increases, the contribution of that covariance to the estimate goes down, right? So using this kernel approach, it's the same thing. You estimate this thing in the middle, the x prime sigma x, but now allow for special autocorrelation of unspecified form. Now, remember what we said the other day, the difference between an autoregressive and a moving average process, one was global, the other one was local. A kernel function, because there's a bandwidth and it stops beyond the bandwidth, is local spatial autocorrelation. So if your process is truly one of global correlation, then cutting it off at a bandwidth may not be such a great idea. Okay, that's something to keep in mind. But it's an easy way out to avoid I mean, this day and age, you don't have to do that anymore, but in the old days, to avoid the estimation of a spatial, using a spatial method. So you just run OLS and stick in hack standard errors, and you have corrected for spatial autocorrelation of unknown form. You run a two-stage least squares with a hack standard errors, and you have corrected for spatial autocorrelation of unknown form. Where this will come in handy is when we run a spatial lag model, and we might suspect that there is remaining autocorrelation in the error terms. We can either model a higher order specification, which we'll see later is kind of messy, or we can say, let's just look at the hack standard errors, and if they're very different from the ones we have originally, let's use them. We may have a problem. If they're not very different, there's no issue there. We're fine, right? So it's the same mechanics. In the OLS case, you say robust equal hack. You do have to specify a kernel weights matrix, and then you can give it a name if you want to. If you don't specify the kernel weights matrix, you can't create the kernel function to do the hack estimation. So it will give you an error. But this is very simple. Everything looks the same. And here are your standard errors. An interesting comparison that I like to make is when you go from white standard errors to hack standard errors. If there is not much difference between the two, that means there isn't a big spatial issue, right? That most of the correction is the correction for heteroscedasticity and not the correction for the spatial part. If there is a big difference between the two, then you know that it's worthwhile looking at the spatial effects. And this all kind of cross-informs each other when you also do specification tests, which we're going to talk about next week. Okay. So this is in the OLS case. Then the same thing in the two-stage least squares case is the same mechanic, and it tells you hack standard errors. These are the weights that were used in this particular case. And then again, you can compare them with the original output for two-stage least squares.